Okay, my friends, this is stunning to say the least. This was from experiments they did in 2015, the Russians in space, and they found the DNA. It looks to me like this is a double helix, and it appears that it's just formed by itself in space. Okay, my friends, as you know, I have the Dipole Electron Flood Theory, and they have just announced that they do feel that electrons are dipoles. This is all brand new. They've always said an electron is just a totally negative particle. Now they say, well, they're looking for this dipole moment. I show it's clearly a dipole, and they've never seen the dark part of it, so that's why they don't understand it's a dipole. But this was done in space. Now I want you to watch this. This is plasma, and what plasma is charged particles, and this is what they do in space where there has no gravity to crush them. They create their own galaxies. This is in a little vacuum chamber with charged particles. They literally create their own galaxies. They do these same spirals that I've seen over and over and over again because they're pushing themselves away from each other. This is the way light spins. These are the charges, and then they collapse. And then you'll see the actual DNA being, they're looking into this right here. Geneticists are also interested in the results, I guess so, because here's what they're going to see in these results is literally DNA shapes appear. You can't see that, can you? Little DNA shapes appear. Look at this. This is just automatically just pops up by itself. All right, that's pretty stunning. You see this? I had it out with this guy. Origins of Research Scan Life. This guy, James Tour. What are the scientific explanations of the origin of life? I tried to show him what it was, and now I'm seeing it could just be spontaneous in space. Now here's what I was really looking at originally, and my friend Jim Bolin, which he'll be in this video or the next one, mentioned, what about that plasma that you were showing that turning into DNA? And I said, I forgot all about it. And I did forget, because I looked at this years ago. This goes back to 2015. Now, all of these crystallization things they injected all of these particles into this vacuum chamber, and they expected them to create like what they call lattices, like squares like this, everything pushing each other away. And see, instead of a clean lattice, they ended up seeing a black hole, and they freaked out, absolutely freaked out. I mean, I don't blame them. This is what happened. It started bouncing around in here, and it pushed all the dark particles to the center and surrounded them with the white particles. Just think about this. Just give yourself 1 second to think about this. How could, what's in that hole? What's in that black hole? That's a black hole. That's what it is. And these are dark particles that are in here, and they are attracting the white particles around it exactly like everything else. We don't see this on Earth because we just see a flat plane of particles attached to the Earth, and all of them bounce back at us with light bouncing into our eyeballs to stimulate our eyeballs. This only attracts. This is dark matter, and it's also dark energy when it's on the move. When it's just sitting here, it's dark matter. When it's moving, it's dark matter and dark energy, because that will slam things and knock down houses, as I will show you. These particles come ahead of that and burn the house up, and then the next, the black comes and knocks it down. You'll see all this in the video. And I thank God for Jim to remind me of this DNA that showed up, because I had forgotten all about it. I'm telling you, I got so many things going on in the research that I'm losing track of things. But this guy here, I want to talk to him about, what does he think about that? What does he think about this DNA showing up? James Tour, I spent 20 minutes on the phone with him, and then he bailed out on me. He said, well, I don't have anything to talk to you about. Well, I'm talking about the origins of life. That's exactly what he's screaming about everywhere. And I am screaming about it too, but I got a different take on it. And he won't discuss it, because he's got this built-in academic idea that he's just going to stick to his guns no matter what anybody has for evidence, and stay away from the evidence. That's the academic in him. Okay, my friends, Roger once again, and Roger Spur that is, and I have Jim Bolin with me, JB, and Jim is he's a geologist basically, and we've talked a lot about the Earth and so forth, and as far as I know, he hasn't had any objections to what I've been saying. Have you had any objections, Jim?
No, I have not.
All right, so you feel the things I'm saying about the Earth are pretty on target?
Yes, sir.
Okay, well, I appreciate that, my brother. Now, he's not just a geologist. He was, I don't know, you're not still working for the government, right?
Not working for the government, no.
Okay. He was a senior environmental scientist and geologist for the government, for the Army, for the Corps of Engineers. And he certified bridges and all that kind of stuff, and dams and so forth and so on. And so he's a scientific guy, let me just put it that way. But this is not really his forte, is the physics end of things, subatomic realm. Very few people dabble in this range because it's incomprehensible now. It just can't be understood because it's just not right. Now, they just came out with this. Have you ever heard of an electron being a dipole? Well, you haven't unless you've been looking at my stuff. Now, they came out today, National Institute Standards Technology, July 7th, 2023. Researchers conducted a record-breaking precision measurement of the electron's electric dipole moment. How could that be a dipole if it's just a negative? It isn't a negative, it is a dipole. And they're starting to sort of come around the edges of this stuff. And I see this is what happens on virtually everything. They just can't speak about it. Now, they're showing exactly what the electron is made of. It's got a dark side and it's got a glowy side. Now, we're going to go into the actual makeup of these particles because we can see them. Now, hold on. Whoops, hold on a second. Hold on. Okay, I bobbled up things a little bit there, I think, but we're back online here, and I am going to show you light because they're talking about sending light down from space. All right, from these light rays coming from space, they want to harvest them out there and beam them down in microwaves. And it's going to require absolutely a stunning amount of work and huge sales and so forth, and it's not going to be practical, I don't think. Let me show you what I think will be practical. We can come back and look at this if you want to take a closer look. Now, like I say, I'm talking with Jim, and he's going to probably be asking me questions if I go over something that's just not obvious. But they want to, the only reason they want to put these things in space is so that 24 hours a day you can harvest sunlight. And then you can beam it down. But, you know, think of the complexity. Now, let me show you what you are harvesting when you harvest light. What do you think you harvest when you harvest light? What is it you're harvesting? Well, you're harvesting the light. Well, what does that mean? What is light? Do you know what light is? Do you know what heat is? Do you know what cold is? Do you know what dark matter is, dark energy? Nuclear fission and fusion, do you know all those stuff? Well, let's go see if we can figure them out. Hold on. All right, so I still got Jim on the line here. Now, and again, hopefully he's going to have some questions. If anything is confusing, I want to try to make it as unconfusing as possible. So, let's start off with what is light? All right, can we see light? And the fact is, yes. Using CMOS, which is complementary metal oxide silicate semiconductors, you can actually see photons. They have, there's absolutely no question about it now. It's proven, and we are showing them right now. And we've been seeing them now. CMOS has been around since, forever. But they've been putting it in the cell phone since 2012 or earlier maybe. But in 2012, Rod Warren figured out and did this. He took light and he accelerated it. And when I saw this, I freaked. Now, how do I know it's accelerating? Well, you can see it, first of all, but let's just see what does a normal wave look like. All right, there it is right there. Now, I'm going to turn the lights off in here so that this brightens up a little bit. Now, what are we looking at here? We're looking at a light wave. Okay, and you say, well, is it a wave or a particle? It's both. They've always said that. It's a duality, particle-wave duality. That means both of them in one package. Why would it be a wave and still be a particle? Well, the particle has a magnetic field around it. Just like if you take a magnet, about an inch away from the magnet, you still have a field. If you push that field through somebody else's field, like all of these particles here, which also have their own fields, they got to get the hell out of the way. Anytime you push two fields together, it's called a Casimir effect, you get glow. And it's push to shove of magnetic fields. So the ones in front are shoving back, this one's pushing forward really hard. Well, you know, it's pushing at the speed of light. They say it's one speed. It's not one speed, not whatsoever. Well, I can show you it's not one speed. You see that speed? All right, just look at it and think about what you're seeing there. It's coming forward. These are pulsed laser pulses. Each one of them contains a number of photons. Just think about it that way. But they all have fields, and they're all plowing through these gases. And what gases are those? Well, your hydrogen, oxygen, carbon dioxide, nitrogen, all that stuff is in the air, which is what's in the air right in front of you. So it starts plowing through there. Well, what happens when you put a venturi in front of something? It's a restriction, it's an accelerator. It's just exactly, literally identical to what you do with a hose. And you put a restriction, and it forces the hose to squirt. And this is exactly what happened. Light is literally liquid. You hear that, Jim?
Well, I hear it. Yeah, I sure do.
Light is literally liquid. And when it comes through, it's in this form. You see it accelerating like crazy? And then it's getting brighter and brighter and brighter, 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 ba-ba-da-boom. Why ba-da-ba-boom? Well, the ba-da-ba-boom happens because of a venturi. And what does a venturi do? It forces the particles to constrict through a slot, just like this. But it's so tight that only the white, which can squish down, goes through the venturi. The black stays on the other side. However, they recombine almost instantaneously. This white right here is what you use to charge your batteries. This is all you want to go into your batteries to charge them up. It has literally no weight, almost whatsoever, that I can determine. But it burns like hell. And what do you want your electricity to do? When you turn on your oven, if you have an electric oven, what happens, John?
Well, it glows.
It gets hot, right?
It gets hot.
Yeah, well, that's the electrons are forcing themselves through other electrons. That's what's going on. It's a resistance. And the more resistance you have and the more current you have, the more glow you have and the more it creates a lot of heat. Now, can we watch this kind of an effect occur? Yes, we can. And we can see it in an atomic bomb. Now, what are we going to be looking at? First of all, we are accelerating light here. We're splitting light, and I'm saying that black separates from the white, and I can show it in a much closer detail, which is precisely, you see the black now? Completely separated from the white, 100%. The only thing that's going through the venturi is the white. But the black comes right back in. See, it snuggles right around the edges. It wants that white back so badly that that's what electricity is all about, is the white being sucked to the black. All right, I always was wondering, is the white pulling the black? No. The black is sucking the white to it. And I can prove all of these things I'm saying. And so that white is always attached to black. Now it's so puffed up, it can squirt through the venturi and actually disassociate from the black. I never believed that would be possible, because a bar magnet, you can't make a bar magnet become not a bar magnet. Once it's a bar magnet, you can cut it 1,000 times, you have 1,000 bar magnets. Now, but now we're down to the spot where there is nothing left to do, so the black can go from the white. So now, we just saw light pushing its way through the atmosphere at the speed of light. Well, my friends, what is this? That certainly is not the speed of light. That is additional to the speed of light, and that is not even in a vacuum, which everything Einstein was talking about was in a vacuum. And I agree, if you put light through a vacuum and there was no resistance to it pushing forward, it may go fast and never slow down if there was no fields to push through. But that's just not the case anywhere. Nowhere on Earth or in space. Nowhere. Space is saturated with particles and dust, and these particles right here, which are light. And what do these particles look like? What does this little white stream coming out of here look like? Well, I'm going to show you what it looks like. This is that little white stream right here. Over here to the left is how this is the neutrino phase. You familiar with that term, Jim? At all, neutrinos?
Yes. Yes.
All right. So the neutrino changes its value, and they can see the same particle keeps changing value, and they just have no idea why. Well, it's concussing against what's in front of it. That means anytime you have an energetic value or even a mass, all that means is how hard you're hitting something. Because the mass of a 1 ounce item just bouncing off of a pillow is an ounce, just basically. But if it bounces off a hard piece of steel, it gains a bunch of energy because it can't absorb that energy. So what's happening is it's changing values because it's bumping up against the stuff that's in front. You see here, it's got a black and a white and a black, like an Oreo cookie. And as it comes forward, this is the same particle right here. And it's sideways, and it's got a white, a black, and a white. And now it's turned into photons. These are photons. There's a bunch of particles coming through here. But the only ones you're going to see real well are the ones coming straight down the center. And they change from this neutrino value to this neutrino value to photons, and then this, I don't know what that is. And then here it explodes into little bits and pieces called muons and electron showers. All right, and that's exactly what it says right here. You see it? Coming through here is electron showers. Here it is right here. A muon neutrino is the black ball. You see the black ball? That's a muon neutrino. And I'm going to tell you right now, that is dark matter, and it's dark energy. Because it does have energy. But they say dark matter has no energy. That's incorrect. Dark matter has dark energy. And I'm going to show you all of this stuff uno momento. All right, you still with me there, Jim?
Yeah, I'm still with you. Is this a good time to ask a question or two?
Yeah, absolutely.
Okay. You know, like on Earth here, we have media like, you know, water, air, that kind of thing. So just to back up a little bit, if I think about the ocean and the water in it as a medium, if there's an earthquake, then there's a wave of energy that goes through that water. And of course the water, the transfer of energy makes the waves in the water. So we have water as a medium. Same thing in air. You know, when the jet goes by and makes the noise, the sound wave from the jet disturbs the air and creates the wave there. So I need you to explain if the light that's approaching the Earth, tell me if I'm understanding you correctly. The light that approaches the Earth is not going through a vacuum, it's going through an energized, rarefied field. In other words, I think what you're saying is space is definitely not a vacuum, and light energy is passing, like say for instance, from the sun to the Earth, or from outer space to the Earth, and rather than that light energy going through a vacuum, it's actually disturbing the media of space. which I think you're saying is an electric field, or it's a field of electric particles, and that's the waveform that we're seeing coming to the Venturi.
Exactly. Yeah, exactly correct. Space is, it's 100% saturated. I mean, so saturated it's unbelievable. It's all the particles from the sun that are coming towards us are particles, and it's saturated with dust, and it's saturated with every kind of debris you can think of. And John Glenn saw all those things. They were called the fireflies.
Right, I remember that.
Yeah, he could see them when he was coming around the sun, because the rays would come down like this. This is the moon, by the way. This is a stunning, stunning picture. This was taken by Rod Warren's nephew, Dylan Carpenter, in Australia. And I don't know what he used to do this, and I haven't been able to make contact with Dylan. But anyway, you can see the fields. All of these fields, for a particle to push through that field, it's got to push that field out of the way. And as those things are coming out, they're slowing down. The light coming to us from these suns and so forth are slowing down so fast, it's unbelievable. And they think it's never slowing down. It is slowing down. These things could be right down the road, literally. It's unbelievable how they think there is nothing in space. And
so what you're showing, when you talk about light coming to the Earth and approaching your Venturi, and it's coming from either the stars, the sun, the moon, or some other object, that's solar energy coming in the form of photons, and it's coming in the form of energy, but it's passing through the space, which is, as you say, loaded with
right there. Here it is right here, Jim. Here it is right here. This is, if you take a photon of light, let's say the sun is over here where I've got my cursor, and it is spitting out all of these particles of light. Those particles of light have to break through these other particles that are in front of them. When they do, they will slow down. This happens to be an exceptional case because it's speeding up, because it's headed towards the Venturi. That's the only reason we see this. I'll show you how it slows down. The blue one here is slowing down. This one coming out of the Venturi. You see it here?
Right.
It's sizzling. It's slowing down. It's obviously slowing down. So I've shown you light speeding up and light slowing down. And light is a photon, and it spins. You see this spinning?
Right.
It's drifting to the left and it's spinning to the right. When it came in hot, it almost wasn't drifting because it was so fast. And then all of a sudden it started drifting as it slowed down. And here's what light looks like when this is it right here. It's spinning. Light is a spinning particle.
Well, that makes sense because when you look at the diagrams of an electromagnetic wave coming towards you, show vibration, in all directions around the midpoint. In other words, it's oscillating side to side. So yes, I understand.
Right, and it does spin. It spins as a particle spinning. So, and it's got to something to do with the right-hand rule, which I think I understand, and I think I have seen one that it was a reverse spinner, and that's created the most unbelievable thing I've ever seen. But anyway, let's. But
the spin, this other spin you're mentioning, is this like in the form of a corkscrew side thing, right? Let's say a beam is coming from the sun towards your Venturi here on Earth. Are you saying it's also making a corkscrew motion around the axis?
All light spins in a circle, just like this. It spins in a circle, just like that.
Okay.
All right, and if you looked at it from the side, now you probably won't be able to see this, but I'm going to show this to the audience here. Sideways, a spring If you stretched it out, it looks like a wave, yes. But that's the particle. If you're looking at it head on, it's the particle spinning. Sometimes it spins to the right, sometimes it spins to the left. But the white ones will not go next to each other. They will push each other out and make these interference patterns. Very, very specific patterns. You see those little patterns? And they call those interference patterns because of a flappy wave. This is not a flappy wave. This is a spinning particle in a single slit. It's not a dual slit. And that's how they go.
I was just getting ready to remark about that. The image that you have there as it approaches Venturi and leaves it is identical to is similar to the double slit photographs we see, except you have a single slit.
Correct.
So it's behaving just like or similar to the way it did in the experiment with the double slit. It's just you have one slit.
Right. The reason you have those interference patterns, which is these white ones, and have a break between the white stripes, is because they hate each other. They go down in the middle, sets up there's nothing they can do about it in the middle. They're stuck with each other, and then they sort of break and break and break and break and break and break, and then they get out to the outside. But each one of these is an interference pattern, and you can't even see how elegant it is until you look at it in this other configuration where you see how many of these patterns there are. Look at this. You see these right here?
Right.
You see that?
Yes, right.
That's pretty incredible, brother. And that's because they're setting up their own interference patterns within their own glob. You see the one that's in the center of each glob is pushing the other ones away, and then it has a big, this is really neat stuff to look at. You really got to pay big, deep attention to it, though.
Right.
All right, now, so what have I shown you? I showed you light here coming through the atmosphere, pushing against the rest of the particles. I showed you light accelerating. I showed you light separating here, the black from the white, and recombining here. That is fission, and that's fusion. All right, that's the holy grail of energy, is to create fission and then fusion. Because what does fission do? Fission says, I want the white. All I want is the white. The white is the only thing that does anything. It weighs nothing and does everything. The black is only there to carry the white. It carries it if it's pushing it, and it sucks it if it's in its gravitational state. It does two things. It pushes and sucks. And that's what blacks do. The whites just burn and have no energy, no mass. Now, can I prove it? Absolutely. Remember I set up the video here, Jim?
Right.
All right, now I've shown this a million times. I love this thing, atomcentral.com. What are we looking at? An atomic bomb. What do I say in the dipole electron flood theory? I say there's a core of blackness, which is, it has all the mass and no burn energy. It's a cold, hard bowling ball. The other part is this. Hold on, I better show you this. I don't know if I did or not. I got lost in these presentations, but here's what the particles look like. I think I did. Here's what they look like. All right, we're going to break the white away from the black, and when it comes forward, the white at the bottom will glow like crazy. When you make the atomic bomb go off, the white, which was coating the black, will all go first, and the white will follow it. And here's exactly what's going to happen. We're going to see this happen. This right here, think of this as a nuclear bomb. All right? Subatomic in this case. They have atomic bombs which can shoot out chunks of things that are like a pound or 2 pounds or 100 pounds. We have light coming. We started with light. We cannot do anything bigger than light. All right, you got that? Now, it comes through here. Remember, one of those particles can glow, but the black can't glow. The black is what they call a fixed particle. It never gets bigger and it never gets smaller. But the white can glow like crazy and it can get small. And here's the proof of that. You see the black and the white?
Yeah.
When they're traveling forward, the one that's concussing, you see it? the white one here with all the little dots in front of it,
Right.
that's the one that's concussing and glowing, and that's what we're going to see in the atomic bomb blast. And then the black is going to be coming from behind. Now, this happens to be a photon. What we're going to be looking at is only the white particles, which are the complete crust, completely encrust the dark core in an atomic bomb. That's what it's all about, fissionable material. You make a dark core with a white crust, and then when you crush it, it's so tight that the particles can't hang in there anymore. They just take off. All the white ones go, and then the black ones follow. Now we're going to watch the house get knocked down. Remember, the white one's going to glow, and then the black one's going to follow. Now, one more time back to here. This is the nuclear bomb going off over here. Out comes the white, and the black is following it and pushing it. Now the house is going to be right here, and it's just going to burn. It's going to vaporize. Burn, 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 burn. And by the time it gets to here, the black hits it, which is a bowling ball, and out it goes. So the white has no mass. It has all the energy. Well, all of the combustive electric energy. Okay, let's do it that way. The white has all 100% of the electric energy. The black has 0% of the electric energy, and it has all the mechanical energy, which is a bowling ball.
That makes sense. The trailing wave, in the Earth's surface, the counterpart to what you're describing is if this was an earthquake rather than an atomic bomb, you would expect to have the compressive wave arrive at the target first. In other words, when there's an earthquake, you get the compressive wave, the pressure wave, and then that's followed by a shear wave. So the kinetic energy is in the shear, is in the trailing part. And I think that's what you're saying.
Well, no question whatsoever. The black is pushing the white, and the black is not glowing. And this was all in the paper that Don Lincoln did for Fermilab, and I tried to work with him about that, and he refused. It's unbelievable. Now, the black is pushing the white to glow like crazy because it went through the Venturi. And you want to see what the white looks like when it goes all by itself? I showed you before, but I'm going to show you what it looks like on steroids. Here's where it goes all by itself. There's nothing but white there, 100% white, 0 black. The other one had the black with it, so it was a little wider on the Venturi and a little bit. But look at this. This is what happens when that white comes through there and hits the black. Every one of these is a black particle. They don't look it, but they are. You see this little white trailer going up here, sizzler?
Yeah.
You see it? It hits a black particle, and then they turn into these Higgs fields. And they're all doing the same thing. They're all finding a black particle to combine with. And this is nothing but white, and that's all we care about, Jim.
Right.
That's all we care about, is to push down into our batteries. Now, I am going to show something here, and you're probably not going to see it. You know about this, right?
Yes, I can see it anyway, but
Okay.
I've seen it before. Yes.
Yeah, you know about this. Now, this is what we should be trying to do, is to harvest free energy based on what you're looking at right here. The laser is pushing just the white, all right? You hear me? Just the white, which has no mass whatsoever, and it just floats through here. As I will show you, it just floats through, and the black goes bam, 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 and slaps the white through, squirting it just like this. I mean, that sucker is blowing electrons in here like on steroids. I call that Higgs on steroids. Now, if we can get in front of this before it hooks back up with the black particles to create Higgs, right up here, and send that white stuff down into the batteries and so forth. That's all you're doing right now. When you charge up a battery, how much heavier do you think a battery gets when you charge it up, Jim? You ever think about it?
I never have. I'm sure it gets a little bit heavier, but I don't know.
It gets virtually no heavier at all. I mean, almost, there is a very, very, very tiny amount of increased weight. And that relates to temperature. And I'm going to tell you a quick story about temperature and electricity and what these particles are. When it gets colder, these particles are gone. When it gets hot, you have an excess of these particles. When you have an excess of them, they want to leave. Nobody wants them around. Get the hell out of here. That's a hot item, and it just sort of bleeds its heat back into whatever will accept it. So that's what heat is, and that's what cold is. Cold wants the white parts. The white parts don't want each other. They just want to get away from me. You follow me?
Well, that makes sense, because if the white is pure energy, then it wouldn't have any mass. It's all converted over to energy.
It has no mass at all. Let's watch this white. As I can show you, it has no mass. Now, we're going to go for the atomic bomb blast. What you're going to see here, again, this is atomcentral.com. I got it running in slow motion, and it was already in slow motion. What I want you to really focus on is all of the stuff in the back here, all of these poles, the wires that are up in here, the house, the shingles, everything that's combustible. And wires, their casings are combustible. These poles are combustible. The shingles in the house. Let's watch what happens when the white, which is the first thing that comes out. All right, the white, as I showed you, I don't want you to forget this. This is it right here. This is our atomic bomb blast. Pow! Out comes the white. It hits the house, which is here. Burn, 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 burn. No movement whatsoever. And then the black hits, and then boom, it's gone. So here we go. First thing you're going to see is an unbelievable glow in the air, which is every electron is being excited. Boom! Now watch, not a single thing moved. Nothing moved whatsoever. All you're doing is combusting. There is no mass to those electrons. Now watch, boom. There's your mass. Now watch what happens now. It turns around and comes back.
Oh yeah.
The reason it comes back is the black particles are lonely. They got rid of all those white particles, and they say, all I want is white particles attached to me.
That makes sense.
And that's what's happening when it comes through the Venturi. They hang around, and there must be a ton of extra ones, because that's all I can think of.
They're trying to recombine.
Exactly. They have to recombine instantaneously, but there has to be a ton of extra ones. Because look at this. You can't imagine, and this is where they're wrong about entangled photons too. These are entangled. You'd call these entangled photons, which means the black are entangled with the white. And two electrons, which are what they call gluons, the black and white together, are attached together, and you might call those entangled. But they're certainly not going to find themselves the same partner they left with, like you go find your wife in a grocery store. No, it comes through here and they smash apart, and over here there's just got to be a ton of extra ones laying around.
It's kind of like a square dance. People get mixed up and then they have to choose another partner.
Yeah, well, as soon as they become so concussed that they no longer can hold on to their black partner, through the Venturi they go, and as they go through, they are being assailed by all of these exact same size black particles. They never change size. They're all identical. You know, you don't see them looking exactly identical, but trust me, they are. And the only reason you can even see them is because they're on top of the white. This never happens, ever, 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 to anything that gives off light, because the only thing it gives off is a white. So the black is always encased in electrons, which are these white particles. That's the new dipole electron flood theory.
Okay, so all right, so we got the dipoles separating into the white and the black. Now, I think you had said the best place to harness the actual energy is maybe just after the Venturi.
Right here, John. Right here.
That's the energy-rich zone there. Now you want to convert that to microwave?
No. That will be raw. That's electricity. This is electricity. Light is electricity. When you shine light on these solar panels, you're getting electricity. Now we're getting it though completely separate. When you get it from light coming down, you have to. They got to be doing something with it, because you're getting both the black and the white particle. You're getting that pusher, and you're getting the white particle in front of it. Which light coming down from the sun is coming down like this with the black, and then whatever the one in front is. And so when that hits the solar panel,
I see.
I know. Well, okay, wait a minute. I know what they're doing with it. I'm being stupid here. What they're doing is the same thing we're doing, only they're using silicon, and we're using transition metals. And so we can harvest much more energy than they're harvesting. And the reason
transition metals,
yeah,
like cerium or something like that.
No, transition metals like the. Well, hold on a second. Let me just show you how easily this happens. Hold on. All right, I'm just going to jump to this quickly so that you got an idea of what's going on with how solar panels work. There's PN junctions, positive, negative junctions, and they're arranging the atoms, and they're like using boron and gallium and some other types of metals within to create what they call a hole or a vacancy. Well, transition metals create holes and vacancies because they have these plus charges. Now, I think they're going to be very attractive to, high energy inputs to these. You know what? I'm not going to go this route. All right, I was going to get real deep into the new materials, but that bores people. There is new materials that they call perovskites, and then there's thin filmed transition metals and so forth that they can spray like a spray gun on these panels. And because they're indoors, they don't have to be outside, they're not in the weather or anything. They can be in our little box that you can carry around with you. You don't have to sign this stuff out of space. Just think about, well, I'll show you what you should be thinking about in a minute, but they're saying this new type of material could change the solar industry forever. Well, let's just go on to see, can we change the solar industry and make it so that anybody can do it? And you don't even need to do it from the solar. They want to get it from the sun. We don't need to get it from the sun. We can make our own by separating the electrons from the muons. All right, I'm going to show you again. All right, remember this now. This is ultra important that you understand that we started with light. This is just nothing but light. This is not deadly. What you want is the electrons coming out of here. If you hold a battery in your hand, you don't get electrocuted. If you shine a light on your hand, you don't get electrocuted. It gets warm. But if you shine light through this venturi, and you can pick up just that white material and send it down through the solar collector, which is these transition metals. You see I put some different colors on here? That's the transition metals, have different colors. And they pick up different frequencies of light. So you don't just get silicon, which has a certain frequency. You don't just get gallium or boron. You get all of these different thin film, because it just penetrates right through there until it gets absorbed. Once it gets absorbed, it pushes itself, because there's no pushback to it. There's no pushback. You saw how it just burnt up the house. Like nothing, was just having a nice day out there for a walk in the park. The house is burning up, and then boom. So if you can get that white past that venturi, it's just going to dribble basically into these batteries. It's going. I can't see any other thing. Now, once it's down here in the batteries, it goes through the photodiode. A photodiode means photons can go only one way through the diode. Which is these PN things. Well, maybe I didn't talk to you about that. But positive negatives are where a diode comes from. And this one here, once it goes through there, it can't come back. So once you collect it down here, you use it for anything you want. And if you think about a battery, just think about charging your 12-volt battery in your car. Now, you could do a hell of a lot of work with that 12-volt battery being charged up, right, Jim?
Oh, that's right. That's right.
Yeah.
Yeah, you could run your headlights,
Well, you could run. You could turn your car over. There's a lot of juice in there. But I'm going to tell you what: when you charge it up, you won't know that there's no extra weight in there. And it's just that there's a ton of these extra white particles that want to find black particles. All the other ones are snuggled up to black ones. And all the white ones are stuffed in there now. And they have no mass, but they're sort of cramped in there, and they want to get out to find, well, the black ones want to suck them out of there is the way it works. And they do it through a wire. Through the air, they will bleed off through the air, but certainly not like through a wire. When you take copper, it has a ton of extra electrons in it already. That's what copper's all about. That's why it's such a good conductor. It has a ton of extra electrons. And if you take a superconductor, listen to this now. This is where it gets crazy. Because when you conduct electricity through copper, you need, well, you know what? I could be wrong about that. There might be a lot of vacancies in that copper where the electrons can wiggle their way through. That could be, because it's a good conductor. I think I was wrong, but nobody understands it anyway. There's no resistance in copper. So, well, there's got to be less electrons. I thought there would be more. Yeah, I'd be honest with you. I've always worked under that assumption until just this instant. I always thought they were pushing them through. They're not. There's just nothing for them to stop them from going through. You finally understand what I'm saying?
Oh yeah, yeah.
So that's why there's no resistance. Resistance is extra electrons. What a moron I was. I can't believe I didn't figure this out until just now. I'm telling you, every minute of my life is a minute of discovery, brother.
Well, that's good.
This happens every day to me. I said, I know this, I know that. Well, no, I don't. But you got to be able to pay attention to what is obvious.
Yeah.
Because listen to this.
You just have to talk it through to them.
Exactly.
Let the light bulb go. Yeah.
Exactly. That's why it's just so important to have somebody to bounce things off of. You know, you're helping me a lot, and you have a good knowledge of a lot of things, so that's important. But anyway, it's when you go through the copper, there has to be a lack of excess electrons. Not excess electrons, a lack. So they will suck through there easily. And I can almost prove this now.
Like your diagram said, like the diagram said earlier, electron holes or vacancies, right? In other words, let me catch up with you here just a moment. So as the light is passing through the Venturi, we've got it split. You got it split, and the white is the pure energy. Now, if that impacts onto something that's copper, I think I'm understanding you to say if that white portion impinges on a piece of copper, then it's going to deposit electrical energy into that copper by transferring electrons into the vacancies that's resident in the copper. Have I gotten that right?
Yes, you do. It will not bounce. When you think of light, think of bounce. Light, the white particle will hit something and bounce. The black particle will bounce off or bounce with it, usually, I would expect. That's my expectation, is normal light hitting things is strictly the white part bouncing off. But if that what it hits can absorb that energy, it might just stick into it and add its electron into that batch of electrons, which is the fabric of the cotton or whatever. Or it might just barely bounce off of there and not really come out fast. But when the blue energy bounces, when you see blue, that was right down tight on the nucleus, and it had to come out of there really hard to come out. Red just barely comes out. Green is in the middle, and I can show you the green and the red together at the same time, right here, going through the same Venturi. You see how brilliant the green is up here?
Right.
And how dim the red is? The red is just not spinning fast enough. And the green hits it so hard it makes it spin this way. They don't spin this way. They spin on their axis according to the Earth. They call it upspin and downspin. And they don't spin and tumble like that, but this does, because the white particle here smacked into the white particle here so violently that it made it tumble. All right, and then a green reconcussed way out here.
Right. It makes sense. Makes sense, right?
Yeah. And here it is again, same thing. These are the same particles. The green and the red, you know, they're all the same particle. I think here's the green going through the same phases. Here's the neutrino phases. See the red, the white, and the black, and the white, and so forth. And here's the photon phase. And here's when it is getting ready to spin. You see the white is getting charged up here?
Right.
It's going to flip to the back, and that white will come in front and start to absorb. And that's what they do. They just go, they keep rolling down the road. That's the muon wobble, they call it. And to think that nothing in space is going to slow down light is it's just not credible at all. And they're saying this to this very day. All right, 75,000 light years away. No, not at all. I don't know how far it is, but it's certainly not like they're saying. Hold on 1 second, Joe. Okay, this is the Large Hadron Collider. They wanted to use this to do what we're doing, photo collider. But we do it pinched this way. They wanted to do it head on. They couldn't figure out how to do it. We're doing the exact same thing, only we're pinching them sideways to create this. They didn't even realize they did this. This is a Feynman drawing, and it's doing exactly what they did, but they're using protons. We're using light, so which is a bazillion times. Well, here it is right here. 100 billion particles they were using, which was big particles. These are protons, and only 25 or so would hit. This is at CERN. So they wanted to do the physics for studying photon collisions. What did I show you? Why it's so important? And they discussed this. They had a special meeting in 1978. They couldn't figure out how to do it. And it says these collisions are very clean. We're colliding photons, elementary particles, not composite ones like protons. They're just getting a splash of debris, really. And they've never even broken even, I don't think. I'm almost 100% sure of that. We should be able to harvest scads of these electron showers. Now, don't forget, the physics case for studying photon collisions. Listen to what that case is. It's just recently been re-examined. Okay, so you see that CERN wants to do this, and they couldn't figure out how to do it. All you got to do is force them sideways. It's just as good as hitting them head on, because the black smashes them. Now, this is the physics for electron showers. Physics of electron showers, and they're doing with protons. They're making proton-protons collision, decaying, and this until they get down to neutrinos and antineutrinos of all flavors, which I just showed you. And then energy from the neutrinos can be from a few hundred giga-electron volts to a few trillion electron volts. That's the white showers. Those are the electron neutrinos, the energy from these neutrinos. Now, that's exactly what I have shown you was the energy from those neutrinos. And that's what they were looking for, is right there. This is fission and fusion. And because this white wants to be so desperately attached to the black, these are not WIMPs. They call them weakly interacting something. These are not weakly interacting particles. These are the strongest interaction you can have. This is electricity as it comes back to the black. That's solid, just exactly like you're going through the wires in your house. And before, when I was talking about copper, it must have less electrons because it conducts so easily. Absolute zero. When you make something go to absolute zero, that's called superconducting. Well, the only reason it's superconducting is there's no electrons in it, so it just flushes right through there, just like it would through the copper. But the copper is at a much more close temperature of what we can work with, and it still has resistance. You can overheat a copper wire, absolutely. The bigger the copper wire, the more flow you get. Okay, so I've been talking with Jim Bolin, and I really appreciate his time and his input. And this is what I'm hoping to do. You saw the energy, you saw the increased luminosity. That's increase in energy. These electron showers, as I showed you, increase to trillions of electron volts in some case, and we separate the white from the black, it's just nothing but energy. And this continuously runs all day long. You don't have to stop it, and part of the energy you did would come back to run the laser and just keep it going. It could be portable. You carry it around, plug any kind of device into it, because you could have it regulated for, the regulator would decide how you're going to use that energy. It's not like, just trust me. You can hit a button and say, I want to have 110 volts, 220 volts, 50 cycle, 60 cycle, AC, DC, or anything. You know, and you have all these different outlets coming out of it. Have it watertight and sealed. You carry it around with you, and there's no big deal. You don't have to beam it out of space, and all these other things they're talking about, fusion. They still have not gotten even close. And you know, for someone not to want to even investigate this, I don't see that as being, you know, good. Especially like because I presented this to Family Lab, and they called me a tinfoil hat guy, but this is the same pictures that they're showing. This is their right from their lab right there, the black one and the point particle. And they say specifically in Don Lincoln's article, said the black one is a fixed particle, never changes size, and has all the mass. The white one has no mass, but it has a huge field. If you don't see that, I don't know what I can say. Did I make my point, you think, Jim?
Yeah, oh, definitely. I mean, it's pretty clear right here in your images.
I don't see how you can miss it. Now, the second thing is, what about dark energy and dark matter? The dark matter has never been seen before because the black balls are always behind the white, and they don't radiate, right? So they don't emit, they don't absorb, and they don't reflect. So if they don't do any of those things, you just don't know they're there unless they obstruct the light of something else, and the light of everything else is on top of that, so they will never obstruct it. The only way we could do it was to make it into this spray and see the little black particles laying on top of the spray. You understand, Jim?
Oh yeah, definitely. That's excellent.
You can see it on top of the white, and that's the only way you could ever see this. So that's why they've never seen the dark matter. That's why they call it dark matter. Now, is there any dark energy there? Well, yes, we know there is. It's a bowling ball energy. It's a knocker-downer energy. It knocked that house down flatter than a pancake. But before that happened, the white particles were ahead of the black particles, and they just fumed it up. I'm having a hard time with that, to be perfectly honest with you, how they could have no mass and have so much energy. I just can't figure it out. I would think it was the other way around. The bowling ball would have all the energy, but it doesn't. It has no energy at all. I think it's absolute zero. Because
bowling balls would have kinetic energy, but see, you're down on the quantum level here, where the particle is at this level. You're talking about the white particles that are complete energy, and the trailing black particles are kinetic. So you would expect most of the energy to be in the illuminated particles. I mean, as far as energy goes,
Yeah, as far as electric energy, I agree, because the black has no electric energy at all. It's an attractor. It's gravity, and the bigger the mass gets, the more gravity it has. It's as simple as that. They know that, but they just don't equate it to being more black mass creates more gravity, and that's why at a certain point you have a black hole, which the white particles get close to it and they can't get away, and they surround it. Did I show you the Russian one?
I can't. Not recently. I could stand to be refreshed on it if you got time.
Hold on, let me see. The Russians did a thing in space, and they used. Hold on. Here's what a regular black hole looks like, and here's the Russian black hole. Hold on. Hold the fort. Help. Oh, here we go. black hole, the Russian black hole. Here's the Fermi lab. I mean the Dirac, just so you can see it. All right, here goes. Now, this is it right here. This is what the Russians created in space. They freaked out. They went freaking crazy, man, when they saw this. Here's what they did. They took a vacuum chamber. And the vacuum chamber, if anybody doesn't know what it is, just means there is no particle whatsoever in there. It's a complete vacuum of supposedly all the particles of dust and supposedly gases is what they say. Now, they injected these white particles in here, but they were just charged bits of dust, tiny, tiny, tiny micron-sized dust with an extra charge on it, which means an extra electron. And when they came in here, they created this black hole with this white coating all the way around it. Now, I am saying that, my friends, is precisely what an atom looks like. The center is a black core, and that's on an atomic scale. Now, I showed you what they're made out of, the black and white, which are these Diracs. All right? They call these Dirac neutrinos. And that's what we're dealing with, the matter and antimatter. And I showed them, well, I know you've seen it, but I'm going to just make sure I ingrain this into you. Here they are right here. Now, each one of these is what they call a gluon, a black and a white together. They've seen them. They know what they look like. They just don't know where they came from or what they really represent, because all they're seeing them is in a bunch of debris. They never see them made from light. That's the beauty of what we're doing. It started with light. We're looking at light. It doesn't get any simpler than that. So this we don't need. So now, this is what they claim this black hole in space is. It creates that black hole just like we saw, and all the white particles collect around it, and they can make that event horizon, and then they can't get back out, and they're stuck around the outside of the black hole. That's exactly correct.
Right, right.
And the bigger the black hole gets, the more white stuff around it. This is the proof of it right here.
Right, right.
And I had all my stuff done, and I showed this with all my other stuff to Don Lincoln at Fermi Lab, and he called me a tinfoil hat guy, and
as I recall, the first time you showed me this, it actually formed the double helix once you allowed that the film to go ahead and you showed the particles going through that black hole. Do you remember that? It formed a double helix in there. It was really amazing.
Well, I'm not sure that I see them spinning. I can see the particles spinning. That's not a problem. But I don't know about the double helix, actually. This is about as close as you're going to see to that. I don't remember that, to be perfectly honest with you, Jim. But they are. I can see the Higgs fields. I got tons of Higgs fields, and but I also do believe that, as you know, I believe in biology, not geology, to speak of. So, who knows? And when you look at this, I'm going to tell you something. I've been looking at this, trying to figure this out. Here we are on Earth, looking up at the moon, the yellow thing. The blue up here, in my mind, is light compressing. You know what the redshift is? It's supposed to be light getting pulled away, so it shifts to the red side. The bottom is getting shifted to the red side, but the top is getting compressed and making it look blue. Now, whatever this stuff is on top of the moon is either on top of the moon or it's between us and the moon. What it is, all I can tell you is wherever you have energy, you have light.
Yeah.
Now look at this. This freaks me out big time. This looks like a pyramid to me.
It does. I see that.
Now, what are these little white things going back and forth to Atlantis. I mean, no, that's not Atlantis, is it? It might be. These are the ships going back and forth, maybe. Who knows? And this...
Hey, I need to take a pause, just a minute.
All right. Okay, we're live now. Hold on. All right, Jim was good enough to remind me about this experiment. I haven't gone back and looked at this in a long time. Remember, this goes back 10 years ago. Well, 8 years ago they did this, but this goes back to well, I guess it was 8 years ago. 2015, somewhere around there. Now, you see what it's showing here, this box? It's saying if the plasma is cooled cryogenically, a DNA shape appears. Wait till you see this. Watch what happens here. Look at this. Look at that.
That's amazing.
This is in outer space. Let me go back again. Look at this, Jim. I want to stop it, right? Because you can actually see the bridges going across. Watch. Here it goes. Whoops. I'm going to go real slow. Watch for it setting up the bridges. Hold on. You know what? I'm going to go
That's
to
a double helix.
25%. Now, I slowed it down a little bit so we can see it. Here goes. Watch, you look at the bars going across, separating out. You see that? You see how perfect that is for DNA? You're right, Jim. I forgot all about this, man.
That's what they ought to rename the God part.
And this was the other one where they squirted in.
God molecule.
Yeah. Now here's what he says. These are the charged particles, and they squirted it in from the side. You see how they're all coming in stripes like this? That's because they hate each other. They come. These are interference patterns in the air. They don't want to be next to each other, so they set up lines, just like in the interference patterns. Now I got it run slow motion. This is in a vacuum chamber in their space station, which has a little bit of gravity to it, but not much. That's why the ball you'll see that it forms is not 100% perfectly round. It's got a little wet flatness because it's still got some gravity to it. So here goes. And again, this is running real slow. They're coming in, setting up their own little lines, and it's coming in like a bullet. All right, and then it's gonna, all these things will mix together and create a big particle soup. All right, so they're watching it, and when it did what it did, they freaked out on Earth. All right, so they're watching these particles swishing around and doing all their little twisty things and precipitating out. See, here you can see the dust particles and beginning of the crystallization process. So they're watching them crystallize. Why? I don't think I showed you this, Jim, but they actually set up big and small particles in the crystals of the particles in here. I should speed it up a little bit. But here's when they swished them in here. Now this is extremely slow motion. So it's coming in, and all these little particles are going to start to settle out. All right, now you'll see them dropping downwards because there is some gravity. There is still some gravity out there. Well, it's being held gravitationally in the pull of the Earth, so that's how much gravity there is. So they're sort of dropping down, but they were going to end up creating a black hole in the center of these white particles, because they all want to push each other away from each other. They hate each other. And here's what it ends up happening. Watch, it's all buzzing around, buzzing around, buzzing around. Now watch what, boom, 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 boom. See it bouncing? Bounce, 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 bounce. And it's pushing all the black into the center. One of the Earth guys couldn't believe it. He locked himself in his office for 3 weeks. Look. And eventually, all of the white, as much of it that's excess, will collect around. All right, That was so unexpected that the guy locked himself in his office for 3 weeks. Locked himself in his office for several weeks. I mean, that's just stunning stuff. Stunning, stunning stuff. And these are what's happening in space. Look at that. See how they push each other away? That's just nothing more than a galaxy. Look at that. They hate each other. That's why they spin. That's why light spins. I showed you how it spins. Anyway, that's all right, Jim, what do you think, buddy? I think Jim had to go. Anyway, I'm going to wrap it up now, and that's the electron flood theory. You still there, Jim? No, I think he had to go. All right, we're calling it quits, and thank you. I love you all.